Back Physics 30. This is the last section in the gravitational field unit, FI1.3, satellites and weightlessness. Using Newton's second law of motion, the universal law of gravitation, and the concept of centripetal acceleration to solve problems involving orbital motions of satellites, and explain the apparent weightlessness of an astronaut in orbit. All right. So, satellite motion. Artificial satellites circling Earth are now commonplace. A satellite is put into orbit by accelerating it to a sufficiently high tangential speed, so a certain v, with the use of rockets as shown over here. So placed because it needs to have a certain speed in order to maintain that orbit, because again, it's constantly falling, but if it's going fast enough, it can maintain an orbital type pattern. If the speed is too high, the spacecraft will exit the orbit. If the speed is too low, it returns back to Earth. Satellites are typically put into circular or nearly circular orbits because such orbits require the least takeoff speed. So it need that specific speed to keep it in that orbit as it's feeling the pull of the Earth. It is sometimes asked what keeps the satellite up. The answer is it's high speed that it must have. If the satellite in orbit stopped moving, it would just simply fall, right? Fall back to the Earth. But at a very high speed, as satellite highs, it would quickly fly off into space if it weren't for the gravitational force of the Earth pulling it into orbit. In fact, a satellite in orbit is constantly experiencing the acceleration due to gravity, but its high speed keeps it in a specific path. For satellites that move in a circle or at least approximate circle, the needed acceleration is v squared over r. If you recall from our centripetal motion relationships, a equals v squared over r. The force that gives a satellite this acceleration is the force of gravity exerted by the Earth. And since a satellite may be a considerable distance from Earth, we must use Newton's law of gravitation for the forces acting on it. When we apply Newton's second law, so we have Fg, and if we use Fc, which I believe I called it Fc, centripetal force, which is mv squared over r, that inward force, they must be equivalent. So Fg, gmme over r squared, and then for centripetal force, mv squared over r. These two masses cancel, of course. Where m is the mass of the satellite, this equation relates the distance of the satellite from the Earth's center. That's a key thing to know. Again, that r is from the center of the Earth, because the Earth is so big, to its speed, v, in a circular orbit. Note that only one force, gravity, is acting on the satellite, and that r is the sum of the Earth's radius plus the altitude or height above the surface in which it's at. So if I rearrange this and solve for v, m and m of the objects in question cancel out. We'll have an r squared and an r. The r will cancel out, and we end up with this if I rearrange that for v. The tangential velocity that an object must have is dependent upon the mass of the object that's circling, in this case Earth, and then the radius, how far it is from the center of that object. Now this could apply to Earth, it could apply to other planets as well, as long as you're looking at the radius and the altitude and the mass of the specific planet in question. And we see that the satellite's speed does not depend upon its own mass. Satellites of different mass orbiting at the same distance above the Earth had the same speed and period, which is interesting. So it depends upon the body you're going around. Geosynchronous satellites. A geosynchronous satellite is one that stays above the same point of the Earth. Because you may have thought, well, how satellites appear just to be sitting in one spot, right? But no, they're constantly moving at a high speed to maintain that orbit. But why does it appear to be above? Well, it can, as long as it is above the equator. Because the center of the satellite orbit is always at the center of the Earth, so it's not possible to have a satellite orbiting above a fixed point on the Earth at any other latitude other than 0 degrees. Because as the Earth is rotating, the satellite is rotating with it. So it appears to be not moving, but it's actually rotating with the Earth along the equator, approximately where the Earth rotates. Above that spot. Geosynchronous satellites are commonly used for TV and radio transmission, for weather forecasting, and as communication relays. So let's look at a question here. the height above the Earth's surface such a satellite must orbit, and then what speed it would have to have. So first of all, there's not a lot of room in this paper. I wish I would have left more, but we'll try to do it all here. So we have this new equation that we just found. V is equal to the constant g multiplied by the mass of Earth over r. Now we need to know height, so we're looking for r, but we don't know the speed of the satellite. That's actually part B that we're going to figure out somewhere over here. So we have to have another way of figuring this out. And in fact, we do. So I could say here from circular motion, I also know that V can be calculated as 2 pi r over t. Okay, so going around in a full day, I could figure out what t is, and I can set both of these, V equals V, so this V is equal to this V. So I know what, and I can rearrange this and solve for r. So first of all, let's get rid of the square root by squaring both sides. Then square this side. 2 times pi, so 2 pi r squared is going to be 2 pi r times 2 pi r, 4 pi squared r squared over t squared. And if I bring all the r's to the same side, so multiply by r, and then multiply by t squared divided by 4 pi squared, I would get this. And then, of course, r would be equal to the cube root of g multiplied by me multiplied by t squared all over 4 pi squared. And I know all of these. So the big G, 6.67 times 10 to the minus 11. Mass of Earth that we have from before, 5.98 times 10 to the 24. Now T I don't have, so I'm going to have to figure that out. So if we look at T being 1 day, so that's what the period will be. The seconds to make one complete revolution around, that is going to be equivalent to 1 day. And 1 day is 24 hours. 1 hour is 60 minutes. 1 minute is 60 seconds. So that gives me 86,400 seconds are what are in 1 day. So 86,400 square. So that's quite a bit to calculate in your calculator. And you should have a cube root button. If you look above your square root button, chances are if you use a shift or second function, it's above there. If you're using a TI-83, I think you have to press the math button. So you'll have to figure out on your particular calculator where it is. So if I press math, yeah, there it is right there, cube root. So you'll have to figure out where to find that in your calculator. What that works out to be is a radius of 4.23 times 10 to the 7 meters from center of Earth. Because remember, the R represents the radius from the center of the Earth. If we're looking at Earth and the satellite, that R is radius of Earth plus altitude. So that R is really that. So to find the height above the Earth's surface, let's see, I'm running out of room here. So a height above Earth, I would have to take this total distance from the center of the Earth and minus the radius of the Earth, which is 6.38 times 10 to the 6 meters, which is from your formula sheet, which I'll post here shortly, or you can look back in your notes. 3.59 times 10 to the 7 meters. So that's the height above the Earth, because again, the R here represents from the center of the Earth. And I think in your assignment number 5, question number 5, I make a little note here. It's going to be very similar to this question, in which we use the 2 velocity equations. The speed the satellite must have, I could either use this speed equation or this speed equation. It doesn't matter. 2 pi r over t, 2 pi, and if I'm using r, I have to use it from the center of the Earth, 4.23 times 10 to the 7, over the period, 86,400. So that's going to give me 3,072 meters per second. If I round it off to 3 sig figs, 3,070. Okay, so it's kind of a big question. I wish I would have left more room for it. All right, so that's satellite motion. So we have this new relationship here, figuring out the speed you must have to orbit, let's say the Earth or another planet, if you know the mass of that planet and also the radius. And here we have another way in which we can figure out the height when we don't know the velocity, by looking at circular velocity equations, such as v equals 2 pi over t and this one here. All right, in part 2, we'll look at the last half of this section. We'll see you again.